We know more about the surface of Mars than we do about the bottom of our own ocean. Beneath the gentle waves that lap against familiar shores, there lies a world so vast, so ancient, and so profoundly unexplored that it makes the darkness between stars feel almost intimate by comparison. Tonight, we descend together into that darkness, slowly, gently, and without hurry, into the planet's last true frontier. The ocean covers approximately 71% of Earth's surface. It holds roughly 1.335 billion cubic kilometers of water, a volume so immense that if you were to pour it out across the landscape of the Moon, it would bury that barren world under a sea nearly 3 kilometers deep. And yet, as of today, we have mapped in high resolution only about 25% of the ocean floor. The rest remains hidden beneath miles of cold, pressurized darkness, more mysterious to us than the cratered plains of distant worlds. This is not a failure of curiosity. It is a testament to the sheer, humbling scale of the thing we are trying to understand. So let your breathing slow. Let the weight of the day lift from your shoulders. Tonight, we will drift through these waters together, layer by layer, wonder by wonder, from the sunlit shallows where life dances in the light, down into the crushing silence of the abyss, where creatures glow in the dark, and the earth itself exhales through volcanic seams. Let us begin at the surface, where sunlight still reaches, and the world feels almost familiar. This is the Epipelagic zone, sometimes called the sunlight zone, and it extends from the surface down to roughly 200 meters below. In the grand architecture of the ocean, it is a thin, luminous skin, barely a fraction of the total depth. And yet it is here that nearly all of the ocean's photosynthesis occurs. Here that the vast majority of marine life we recognize makes its home. The reason is light. Sunlight penetrates seawater, but not very far. Even in the clearest tropical waters, the intensity of light drops dramatically with every meter of depth. By the time you reach 200 meters, less than 1% of surface sunlight remains. And so everything that depends on the sun, from the microscopic phytoplankton that produce roughly 50% of the oxygen in Earth's atmosphere, to the great whales that feed upon the food chains those tiny organisms support, is concentrated in this narrow, glittering band. Consider the phytoplankton for a moment. They are single-celled organisms, most of them too small to see with the naked eye, and yet collectively, scientists estimate they generate between 50 and 80% of the oxygen produced on Earth each year. Every second breath you take may owe its existence to these invisible, drifting cells. They float in the upper ocean by the trillions, absorbing carbon dioxide and sunlight, quietly performing the same photosynthesis that trees and grasses perform on land, but on a scale that dwarfs every forest on the planet combined. This sunlit layer is also where the ocean breathes. Gases exchange between atmosphere and sea at the surface, driven by wind and wave and temperature. Carbon dioxide dissolves into the water. Oxygen escapes into the air. Heat from the sun warms the upper meters, creating a layer of warm water that floats atop the colder depths below, a boundary known as the thermocline, where temperature drops sharply and the light begins its long surrender to the dark. Lie still and picture it, a world of blue and gold, alive with motion, and just 200 meters thick. Now we sink deeper, past the thermocline, past the last fading rays of blue, into the Mesopelagic zone, the twilight zone of the sea. This region stretches from 200 meters down to roughly 1,000 meters, and it is here that daylight finally dies. At first, there is still a faint, ghostly glow, an indigo haze that feels more like a memory of light than light itself. But as you descend further, even that memory fades, and you enter a world where no photosynthesis is possible, where the only illumination comes from the creatures themselves. This is the realm of bioluminescence. Roughly 90% of the animals living in the Mesopelagic zone are thought to produce their own light through chemical reactions involving a molecule called luciferin and an enzyme called luciferase. The light they create is typically blue or green because these wavelengths travel farthest through seawater. Some use it to attract prey. Others flash it to startle predators. Some produce light to communicate with potential mates across the gloom. And some wear it as camouflage, a strategy called counter-illumination, where an animal lights up its belly to match the faint glow from above, erasing its own silhouette from the eyes of hunters lurking below. The Twilight Zone is also home to what scientists call the greatest migration on Earth, though it happens not across plains or through skies, but vertically, through water. Every evening, as darkness falls across the surface, billions of small fish, squid, and zooplankton rise from the Mesopelagic zone toward the sunlit shallows to feed under cover of night. Every morning, as the sun returns, they descend again, retreating into the safety of the deep. This diel vertical migration, as it is known, moves an estimated biomass of billions of tons each day. It is a pulse, a breathing rhythm of the ocean itself, and it happens in near silence, in near darkness, largely unseen by human eyes. It is one of the most massive animal movements in the history of life on Earth, and most people have never heard of it. Let that thought settle gently, like a creature sinking back into the dark. Below 1,000 meters, the ocean becomes something else entirely. This is the Bathypelagic zone, the midnight zone, and here there is no light at all, not a trace, not a whisper. If you were to descend to this depth and turn off every instrument, every lamp, you would experience a darkness more complete than anything available on the surface of the Earth, a darkness that is total and absolute, unbroken by stars or moon or the faintest horizon glow. The water temperature here hovers just above freezing, typically between 0 and 4 degrees Celsius, and the pressure is immense. At 1,000 meters, the water column above you exerts approximately 100 atmospheres of pressure, roughly 100 times the pressure you feel standing at sea level. At 4,000 meters, the deepest reach of this zone, the pressure climbs to 400 atmospheres. Under such force, gas-filled spaces collapse. Human lungs would compress to a fraction of their volume. The physics of survival down here are fundamentally different from anything on the surface, and yet, life persists. The creatures of the Midnight Zone have adapted in extraordinary ways. Many have lost their eyes entirely or reduced them to vestigial remnants, because in a world without light, vision offers no advantage. Instead, they rely on other senses, detecting vibrations in the water through lateral line organs, sensing the faintest chemical traces dissolved in the current. Some have evolved enormous mouths and expandable stomachs, because food is scarce and unpredictable in the deep, and when a meal arrives, it may be the only one for weeks or months. The black swallower, a fish rarely longer than 25 centimeters, can consume prey more than twice its own length and 10 times its own mass by distending its stomach into a translucent balloon. The anglerfish dangles a bioluminescent lure from its forehead, a tiny lantern in the void, patiently waiting in the dark for something curious to come close. There is a quietness to this world that borders on the sacred. No wind, no wave, no sound, but the slow, rhythmic pulse of deep ocean currents moving water that may not see the surface again for 1,000 years. Breathe slowly. You are safe. The darkness here is not threatening. It is simply vast and patient and very old. Deeper still, past 4,000 meters, we enter the Abyssopelagic zone, the abyss. The word itself comes from the Greek abyssos, meaning bottomless, and for much of human history, that is exactly what people believed the deep ocean to be, a featureless void without end. We now know this is not true. The abyssal plain, as it is called, covers roughly 50% of Earth's entire surface, making it the single most common landscape on the planet. And yet, it remains less explored than the face of the moon. The abyssal floor is not empty. It is blanketed in a fine, soft sediment composed of the remains of organisms that lived and died in the waters above, a slow, continuous rain of organic matter that scientists call marine snow. Each flake is tiny, sometimes no larger than a grain of sand, and each one may take weeks to drift from the surface down to the abyssal floor. Over millions of years, this gentle snowfall has built up layers of sediment hundreds of meters thick in places, a geological record of life and climate stretching back tens of millions of years. Within these sediments live communities of organisms so sparse and so slow-moving that they seem, to human perception, almost frozen in time. Polychaete worms, sea cucumbers, tiny crustaceans, all subsisting on the meager calories that filter down from above. Their metabolisms are profoundly slow. Some deep-sea organisms grow so gradually that a creature the size of your thumb may be decades old. And scattered across the abyssal plain are manganese nodules, roughly spherical lumps of mineral that form over millions of years as dissolved metals in the seawater slowly precipitate around a nucleus. A shark tooth, a fragment of bone. A single nodule the size of a potato may have taken between 3 and 10 million years to form. They sit on the seafloor in vast fields, silent witnesses to the deep patience of geological time. This is a landscape measured not in human years, but in epochs. It does not hurry. It does not change quickly. And tonight, neither do you. Let yourself rest in that slowness. Let the abyss hold you the way it holds the sediment, gently, quietly, without rushing toward any destination at all. And yet, beneath even the abyss, there is one more realm. The Hadal Zone, named for Hades, the ancient Greek god of the underworld, begins at roughly 6,000 meters and descends into the deepest trenches on Earth. These are not broad expanses of flat seafloor, but narrow, plunging chasms, carved where one tectonic plate slides slowly beneath another. The deepest of them all, the Mariana Trench in the western Pacific, reaches approximately 10,935 meters below the surface, at a point known as the Challenger Deep. The pressure there is staggering, roughly 1,000 times the atmospheric pressure at sea level, or about 1,086 bars. Imagine the weight of an entire column of ocean, nearly 11 kilometers tall, pressing down upon every square centimeter of your body. And yet, even here, life persists. In sediment samples collected from the bottom of the Mariana Trench, scientists have found tiny single-celled organisms called foraminifera, as well as communities of bacteria thriving on chemicals seeped from the Earth's interior. Small crustaceans, known as amphipods, pale and translucent, have been observed scavenging these lifeless depths. Their bodies exquisitely adapted to pressures that would crush most surface-dwelling organisms. The Hadal Trenches are among the least explored places on Earth. Fewer people have visited the bottom of the Challenger Deep than have walked on the surface of the Moon. The first crude descent was made in January of 1960, when Jacques Piccard and Don Walsh piloted the Bathyscaphe Trieste to the trench floor, spending roughly 20 minutes there before ascending. More than 5 decades passed before filmmaker and explorer James Cameron made the second solo crude descent in March of 2012. These trenches remind us, with quiet insistence, that the deepest mysteries of our own planet remain closer than the stars, hidden not in outer space, but in the silence beneath the waves, waiting patiently in the dark. Now, let us leave the vertical column of the open ocean and drift towards something altogether different. A landscape hidden along the mid-ocean ridges, where the Earth itself breathes heat and chemistry into the water. Hydrothermal vents were first discovered in 1977 along the Galapagos Rift in the eastern Pacific, and they changed our understanding of life on this planet forever. Before that discovery, scientists assumed that all complex ecosystems ultimately depended on sunlight, on photosynthesis, on the slow green machinery of plants converting light into energy. But here, in total darkness, at depths of roughly 2,000 to 3,000 meters, researchers found thriving communities of organisms clustered around superheated plumes of mineral-rich water. The vents form where seawater seeps down through cracks in the ocean crust, is heated by magma chambers below, and rises back to the seafloor at temperatures that can exceed 370 degrees Celsius. As this superheated fluid meets the near-freezing ambient water, dissolved minerals precipitate out, forming towering chimney-like structures, sometimes called black smokers, their dark plumes thick with iron sulfide and other compounds. The foundation of life here is not sunlight, but chemosynthesis. Specialized bacteria and archaea oxidize hydrogen sulfide and other chemicals streaming from the vents, producing energy in a process that mirrors photosynthesis in principle, but requires no light at all. These microbes form the base of an extraordinary food web. Giant tube worms, some reaching over 2 meters in length, have no mouth and no digestive system. Instead, they harbor chemosynthetic bacteria within their bodies, in a symbiotic relationship so intimate that neither organism could survive without the other. Pale crabs and shrimp graze along the chimney walls, and ghostly white octopuses have been observed drifting through the warm blooms. Consider for a moment what this means. Life does not require the sun. It requires only energy and chemistry and time. The discovery of hydrothermal vents reshaped not only marine biology, but also our thinking about the origins of life itself. One leading hypothesis, known as the alkaline hydrothermal vent theory, proposes that life on Earth may have begun not in some warm, sunlit tidal pool, as Charles Darwin once imagined, but deep beneath the ancient ocean, at structures similar to the vents we find today. This idea, championed by geochemist Michael Russell, beginning in the late 1980s, suggests that natural chemical gradients across thin mineral walls and alkaline vents could have provided the energy needed to drive the first simple metabolic reactions billions of years ago. The logic is elegant in its violence. Early Earth, roughly 4 billion years ago, had an atmosphere rich in carbon dioxide and an ocean that was mildly acidic. Alkaline fluids rising through the crust would have met that acidic water at the seafloor, creating a natural proton gradient across porous mineral structures. A gradient remarkably similar to the one that powers every living cell today, through a process called chemiosmosis. Some researchers propose that within these tiny mineral compartments, simple organic molecules could have concentrated, reacted, and eventually given rise to the first self-replicating systems, the distant ancestors of all life on Earth. This remains a hypothesis, not a proven fact, and other origin of life theories exist, including those involving surface geothermal pools, or even delivery of organic compounds by meteorites. The question is far from settled, and yet the deep ocean vents offer something profound to contemplate. If life can begin in total darkness, sustained only by the slow chemistry of rock and water, then the universe may be far more hospitable to living things than we once imagined. Every icy moon with a subsurface ocean, every world with geological activity and liquid water, becomes a place where the spark of life might quietly catch. The ocean floor whispers to us of possibilities far beyond our own small planet. Let us rise now, slowly, gently, away from the ancient ridges and the plumes of heated water, and turn our attention to something vast and often overlooked, something that connects the deep ocean to the surface and to the very breath you are taking right now. The ocean is not still. It moves in great, slow rivers of water that encircle the globe, a system known as thermohaline circulation, driven by differences in temperature and salinity. In the North Atlantic, near Greenland and Iceland, cold winter air chills the surface water, and as sea ice forms, salt is excluded from the crystals and left behind, making the surrounding water denser and heavier. This cold, salty water sinks, plunging to depths of several thousand meters, and begins a long, silent journey southward along the floor of the Atlantic Ocean. It flows past the equator, around the southern tip of Africa, and into the Indian and Pacific basins, where it eventually warms, rises, and begins its slow return to the surface. Scientists estimate that a single parcel of water completing this full circuit, sometimes called the global ocean conveyor belt, may take roughly 1,000 years to make the journey. 1,000 years of silent movement through the dark, carrying heat and dissolved gases and nutrients from one hemisphere to another, connecting tropical warmth to polar cold, in a planetary embrace so slow it is nearly imperceptible. This circulation is profoundly important. It distributes heat across the globe, moderating climates and making much of northern Europe far warmer than its latitude alone would predict. It also draws carbon dioxide from the atmosphere into the deep ocean, where it can remain sequestered for centuries. The ocean, in this way, breathes for the planet, inhaling warmth, carbon at the surface, and exhaling it a millennium later in some distant, quiet corner of the deep. It is a rhythm almost too large and too slow for us to feel, and yet it shapes everything. As we ascend through the water column, consider the extraordinary substance through which we travel. Seawater itself, that ancient and endlessly circulating fluid that connects every shore to every other shore on Earth. The ocean is not still. It has never been still. It moves in patterns so vast and so slow that they were invisible to us for most of human history. And yet they govern the climate of every continent, the rainfall over every field, the temperature every winter night. These are the great thermohaline currents, driven by differences in temperature and salinity. And together they form what oceanographers sometimes call the global conveyor belt. In the North Atlantic, dense, cold, salty water sinks near Greenland and Iceland, plunging thousands of meters to the abyssal depths, where it begins a journey southward along the floor of the Atlantic basin. This deep water creeps past the equator, rounds the tip of Africa, and eventually enters the vast basins of the Indian and Pacific Oceans, where, over centuries, it slowly warms, rises, and begins its long return to the surface. The full circuit of this overturning circulation takes roughly 1,000 years. Water that sank in the Norwegian Sea during the medieval period is only now resurfacing in the tropical Pacific. Consider that, a single parcel of seawater, older than most cathedrals, quietly completing a journey it began before the printing press was invented. This circulation carries not only heat, but also dissolved gases, nutrients, and carbon dioxide from the atmosphere into the deep ocean, where it may remain sequestered for centuries. The ocean has absorbed approximately 30% of the carbon dioxide humanity has released since the Industrial Revolution, and roughly 90% of the excess heat trapped by greenhouse gases. In this way, the sea has been quietly buffering the planet, absorbing consequences that would otherwise have already transformed the atmosphere beyond recognition. And yet this buffering comes at a cost, one we are only beginning to understand, as the chemistry of the ocean itself slowly shifts beneath the waves. That cost is ocean acidification, a quiet chemical shift that has been unfolding beneath the surface for more than 2 centuries, accelerating with each decade of rising emissions. When carbon dioxide dissolves in seawater, it reacts with water molecules to form carbonic acid, which then releases hydrogen ions, lowering the pH of the surrounding ocean. Since the beginning of the industrial era, the average pH of surface seawater has dropped from approximately 8.2 to approximately 8.1. That may sound like a negligible change, but because the pH scale is logarithmic, this represents roughly a 26% increase in hydrogen ion concentration. A significant shift in ocean chemistry occurring far faster than at any point in at least the past 66 million years. For creatures that build shells and skeletons from calcium carbonate, corals, mollusks, sea urchins, certain species of plankton, or coccolithophores, and foraminifera, this change is profound. As the water becomes more acidic, it holds fewer carbonate ions, the very building blocks these organisms need to construct their protective structures. Some laboratory studies have shown that under projected future conditions, the shells of pteropods, tiny free-swimming sea snails, sometimes called sea butterflies, begin to dissolve. Imagine the implications. Creatures that have drifted through the world's oceans for tens of millions of years, suddenly unable to maintain the integrity of their own bodies. And these are not obscure organisms. Pteropods are a vital food source for fish, seabirds, and even some whale species. Coccolithophores, each one smaller than the width of a human hair, collectively produce a significant fraction of the ocean's calcium carbonate and play an important role in the carbon cycle. Their decline could ripple outward through food webs in ways we cannot yet fully predict. The ocean has always changed, of course. Its chemistry has shifted across geological time in response to volcanism, weathering, and the slow dance of tectonic plates. But the pace of the current change is what concerns scientists most. Not the direction of the shift, but its breathtaking speed. And yet, even as we reckon with the ways the ocean is changing, we must acknowledge how astonishingly little of it we have explored. By most estimates, more than 80% of the ocean floor remains unmapped by modern high-resolution sonar, unseen by human eyes or robotic cameras. We have better topographic maps of the surface of Mars than we do of the seabed beneath the Pacific. The reason is not a lack of curiosity, but a matter of sheer, overwhelming scale and difficulty. The ocean covers approximately 361 million square kilometers. Its average depth is roughly 3,688 meters, and its deepest point, the Challenger Deep in the Mariana Trench, reaches nearly 11,000 meters below sea level. At those depths, the pressure exceeds 1,000 times atmospheric pressure at the surface, a force that would crush most structures designed by human engineering. Sunlight, the tool upon which so much of our exploration depends, vanishes entirely below about 1,000 meters. To explore the deep ocean, we must bring our own light, our own pressure vessels, our own life support, venturing into an environment as hostile and alien as outer space. And yet, every expedition returns with discoveries. New species are found with striking regularity. The Census of Marine Life, a decade-long international effort completed in 2010, catalogued approximately 250,000 known marine species, but estimated that many hundreds of thousands, perhaps over 1 million, remain undiscovered. In the Hardle Trenches, the deepest zones of the ocean, researchers have found amphipods, snailfish, and microbial communities thriving under pressures that were once thought incompatible with complex life. In 2019, Victor Vescovo piloted the submersible limiting factor to the bottom of the Challenger Deep and observed, alongside extraordinary life forms, fragments of plastic waste, a reminder that our influence reaches even where our understanding does not. The ocean holds its secrets loosely, offering them to anyone willing to descend into the dark. Perhaps the most remarkable frontier the ocean has revealed in recent decades lies not in its geography, but in its sound. The ocean is a world of sound in ways that few terrestrial environments can match, because water transmits acoustic energy roughly 4.5 times faster than air, and with far less attenuation over distance. A low-frequency call produced by a blue whale can travel hundreds, even thousands of kilometers through the deep sound channel. A layer of water, typically found between roughly 600 and 1,200 meters depth, where temperature and pressure create a minimum in sound speed, causing acoustic waves to refract inward and propagate extraordinary distances with minimal loss. This channel, sometimes called the SOFAR channel, was first described in the 1940s, and during the Cold War, it was exploited by military hydrophone arrays designed to detect submarine movements. When scientists later turned those same instruments towards natural soundscape, they discovered a world of astonishing acoustic complexity. Our songs of humpback whales, which can last for hours and evolve over the course of the breeding season, are among the most intricate vocalizations produced by any animal on Earth. Fin whales produce deep, repetitive pulses near 20 Hz, below the threshold of most human hearing, that may carry across entire ocean basins. Snapping shrimp colonies generate a collective crackling so loud and so constant that it forms a persistent background noise across tropical and subtropical waters. Fish produce clicks, grunts, and drumming sounds using swim bladders, and some coral reef ecosystems are so acoustically rich that larval fish use the sound of a healthy reef to navigate toward it from the open sea. We are only beginning to catalogue this symphony, and already we know that human-generated noise from shipping, sonar, and seismic surveys can interfere with it in ways that disorient, stress, and sometimes physically harm marine life. The ocean speaks ceaselessly and beautifully, if only we learn to listen. The hydrothermal vents that punctuate the mid-ocean ridges were only the beginning of a much deeper revelation, one that has quietly reshaped our understanding of what it means to be alive on this planet. Beneath the seafloor itself, in sediments that have lain undisturbed for millions of years, scientists have discovered microbial communities existing in conditions once thought to be utterly incompatible with biology. These are organisms that metabolize at rates so slow they almost defy the word metabolism, dividing perhaps once every 100 years, or once every 1,000, persisting in a state that hovers somewhere between life and dormancy, in a way we do not yet fully understand. Drilling expeditions conducted by the Integrated Ocean Drilling Program and its successors have recovered living cells from sediments more than 2.5 kilometers below the ocean floor, in temperatures exceeding 100 degrees Celsius, under pressures that crush most laboratory equipment. Current estimates suggest that the deep subsurface biosphere, much of it oceanic, may contain as much as 10 to 20% of all microbial biomass on Earth, though these figures remain a subject of active scientific debate and refinement. And yet, what strikes the imagination most deeply is not the sheer quantity of this hidden life, but its patience. These organisms do not chase energy the way surface life does, with its urgent rhythms of feeding, fleeing, and reproducing. Instead, they endure, drawing vanishingly small amounts of chemical energy from the minerals around them, existing on a timescale that makes the oldest bristlecone climb seem hurried by comparison. Some researchers have proposed that this style of existence, this slow, mineral-fed persistence in the absence of sunlight, may represent one of the earliest modes of life on Earth, a whisper from the very beginning of biology itself. Consider for a moment what that implies. It suggests that the deepest ocean is not merely a repository of ancient geology, but a living archive, a place where the strategies that sustained the first cells may still be quietly at work, unchanged across billions of years of planetary history, patient beyond all reckoning, silent beyond all hearing. So, the ocean becomes something more than a body of water. It becomes a mirror, held up to every discipline of human inquiry, a single vast system in which physics, chemistry, biology, geology, and climate science converge and refuse to be separated. The currents that carry warm water from the tropics to the poles are driven by differences in temperature and salinity. A planetary scale circulation, often called the thermohaline conveyor. And this circulation, in turn, shapes weather patterns over entire continents, influences the productivity of fisheries thousands of kilometers away, and buries carbon in the deep for centuries. Disruption of this system, which paleoclimate records suggest has occurred during past episodes of rapid warming, could alter rainfall patterns from the Indian monsoon to the Sahel, a reminder that the ocean's influence extends far beyond its own shores. Across millions of years, the slow opening and closing of ocean basins through plate tectonics has redirected currents, reshaped coastlines, and fundamentally altered global climate. The formation of the Drake Passage between South America and Antarctica, roughly 30 to 40 million years ago, allowed the Antarctic circumpolar current to isolate the southern continent, contributing to the build-up of the vast Antarctic ice sheet that persists to this day. The ocean, in this light, is not merely responding to the planet's changes. It is, in many ways, orchestrating them, acting as both memory and engine, storing the consequences of past events, while simultaneously shaping the conditions for what comes next. Even the oxygen you are breathing as you listen to these words owes its abundance, in part, to the ocean. For marine phytoplankton are responsible for producing roughly half of all the oxygen generated on Earth each year. Every second breath, so to speak, is a gift from organisms so small they are invisible to the unaided eye, drifting in the sunlit surface waters of a world that is, at its heart, an ocean world. Somewhere tonight, those phytoplankton are still at work, building oxygen molecule by molecule, as they have for billions of years, indifferent to whether anyone is awake to notice. And so, for now, we rest here, suspended somewhere between the surface and the deepest dark, held by the weight and the silence of water that has been flowing across this planet for more than 4 billion years. The ocean does not ask for your attention. It does not demand your understanding. It simply continues, vast and patient, and older than every story ever told. Let your thoughts dissolve like marine snow, drifting slowly, softly, downward through the dark. Let your breathing become the tide, rising and falling without effort, without thought. You have traveled far tonight, through zones of light and shadow, through pressure and silence and time. And now, there is nothing left to do, nowhere left to go. Only this quiet, only this stillness, only the deep and endless sea, carrying you gently into sleep. If this journey brought you any peace tonight, you might consider subscribing, so that the next time sleep feels far away, another voyage will be waiting for you here. Next time, we will descend even deeper into the Haddle trenches, where the earth cracks open and life clings to the impossible. Leave a quiet thought in the comments if you like. Rest well.